Great. So the idea is like really something you need to know about for event streaming. I think Neil, you've done a fantastic introduction. Thank you very much for that. I am core team member of Symfony, mostly on my work for the Symfony Messenger component. And this talk is kind of like my duty back to kind of explain all the things that will go wrong by using things, asynchronous things. That's really what this talk is about. First, we really are going to briefly, I think it's going to take 10 minutes, no more, just trying to, for me to give you an idea of what is a streaming or an even streaming architecture is and what are the benefits. And then you go really straight into the consequences of living this dream of basically managing a distributed system when we've got some stuff that happens directly when a user does something in the website and something that happens in the background in a worker. So the short version is that there are amazing benefits, but there's plenty of things that will go wrong, and I'll show you how to not get into these traps. So why is it interesting, just like after all? So we're gonna just take a very simple example that might have happened to many of you, which is, well, you have a product that works, it's great, and then your product scale, and then you actually start to split your product into multiple services. It turns out that you actually have a team which is multiple, like smaller teams. You have like 20 engineers, or maybe 10 is the time to split, and that's great. And we are in an e-commerce website, and you might have a basket service, an order service, a payment service. They might just be your things, but they can also be the different services. You can see them as for example, the payment service can just be Stripe, right? It's just the idea that you start to have multiple services talking to each other. That's a disclaimer. Just don't do that if you are like 5 developers. But just like, yeah, if you go into this moment, that's what happened, which is great. Now, you probably use HTTP to have like services talking to each other. The baskets kind of like triggers an order, for example, or something like that, and then you can pay after, or the order gives information to the payment service around like how much we need to pay, or the constraints and whatsoever. And what you need to do is to say, hey, I have an amazing new feature idea, which really deserve its own service. It's really an entire logic around discounts. You want to introduce targeted discounts. And it turns out the discounts are about, you really want to maximize the chances of these discounts to work. That's why you do this big project, which is a new service and whatsoever. So this discount service will actually need to have an understanding of what are the products that users have put in their basket, but they never bought. How many orders did they do before? What did they put in their orders? What did they buy? And also it needs to know like how did they pay, because it turns out that actually potentially customers using Amex, you don't want to give them discounts because actually it costs you a lot of processing fees and whatsoever. Anyway, you've got all these data points that kind of like spread across the service or the services, and then you need these in your discount service. The caveat is obviously if you go into this system idea, you will have various different services. If you're lucky and then all of the services here are yours and you have a central database, that might not be the case, but it's really unlikely that you have made this technical decision. So we'll assume that the data is really localized to each service. So how do you make into creating this discounts feature? Well, we've got the first option, which is this discount service now needs to pull the data, all of the data points that we've discussed via an HTTP API, HTTP RPC, whatever you've choose. It pulls the data from the services. So there are a bunch of like caveats, and we're going to focus really on the what is not ideal from this approach. Is that there is a lot of data that is going to be moved. Not necessarily at the moment of trying to figure out a discount, but every single time you want to do a computation that is about, should I give discounts to this user? You need to pull all this data again and across to your service. It's a lot of data being moved. The second main problem, and obviously, sorry, I didn't say that, but the conclusion or the consequence of moving a lot of data is performance problems. It is unlikely to scale the net. The second thing is that your discount service will only be able to work if the 3 other services are available. Their API is available to be queried. That's what is called a cascading failure. A problem in multi-services architectures. You really do not want the inability to create discounts or to think about or to prepare discounts or like to figure out which discounts might be sent. You don't want an ability to do that if the payment provider is down, for example. That makes no sense. In this situation, we would have such a thing of cascading failure. And then the third interesting point is that actually discount, in order to get this information, needs to know where it is. We might be completely used to that idea, but it's really fundamental constraint we put in the system, which is discount knows exactly that this information is in this service, that this is the DNS name, this is how I authenticate for it. There's plenty of information around where the data live, which means that we are not super flexible. At some point where we realized that actually going microservices might have been a mistake, and we actually merged payment and order, because they're tightly coupled together, or order basket, doesn't matter. When we do architectural changes, actually that was it worked very well, and then we split services and so forth. Then it means we need to now refactor all the clients, so the discount. If any of the 3 boxes change, we need to refactor discount so that it gets the information somewhere else. Not ideal at all, actually. The second approach is the idea of like batch processing. You can actually, you have like all this information that might be sort of like compiled by each service every day, every night, whatsoever. The problem is that it is rare that incremental. So there's like, even with batch, you have 2 options, which is either you batch everything, like all the orders that have happened so far, all the different payments. That's the simplest option, but you actually provide like so much duplicated information as well, right? So every single night or every single time you process that batch, you need to read through all the orders that have happened throughout the history of your system. It's not really efficient at all. And then it's not in real time really. So if one of your requirements is actually to say, well, I want to have a discount just straight after they've did an order or something, because we know it really massively increased the conversion rate of this discount being used, well, that's not going to work. If you are in a product situation where you don't need real time, great, that might not be a problem. But that's a fundamental technical and architectural choice as well. That's the kind of like story of you need to wait a few days for your marketing preferences to be distributed across the system. And the third one is really about if you sort of try to counterbalance the problem of having lots of duplicated information in your batch by doing incremental file changes or file batches. So you might actually just create files, CSV or like whatever files that contain only the orders of yesterday. But that is also a massive ball ache to actually manage in the entire system, because now you need to have this understanding of the order of the batches. You need to have this understanding so that when you receive batch files, you need to know whether you've consumed previous ones or not. It is actually there's so much stuff that can go wrong with these files. Then it might not be ideal, or it's probably not the best solution when you can avoid it. And that's where there's this great area, which is event streaming. The concept is that actually you have small data points, so all the things around, hey, a user has paid with Amex, or a product has been added to a basket, all this information flows in real time as events between each systems or each service. So some services create events, some services consume events. The interesting property of that is that actually the services, in order to receive an information, they just need to know which event they care about and where is this place to get the events, which is likely to be a central message bus in the middle. You don't need, as a service, to actually know which other service produced the event. If they're refactorings, whatever, it doesn't matter to you. And you have, in theory, a much higher availability, because even if one of the other services is not working, you can already have, like, you already have the information because you've received all the events already. So you will actually create your own state as a discount service to track all the things you care about from the event. And then it means you don't need to ask all these various different services when you need to make some decision and do some logic. Obviously the caveat is now that your message bus is now one of the most critical part of the system. So that's a balance, but we know pretty well how to make a message bus extremely high available. We know less well how to make many different services, all of them high available, because we actually push much more often bugs to these services than in the message buses. Before we had end-to-end test. Now, there is a fourth interesting thing, and very, very interesting property, which I've explored a lot at Birdie, and we are now in such a system for like 2 years, and it's really, really useful to us, is the idea that the actual message bus can do persistence as well. So what it means is that if you have, and what I'm naming here is the Kafkas of the world. And the concept is that this is message bus, you actually push events to it, you have consumers, but on top of that, the message bus keeps the messages in the bus. And then now what you do is you create a new service called discount. Well, you don't even need to do any migration of data from what has happened in the last month, if that's something that is important for your discounts logic, which is very likely. You don't need to do that. All you need to do is to consume all the events that are already here in the bus from the history of your system's time. And you create your local state, and you have everything that you need to go. And that's it. You don't need to do a mix of, like, I'm going to subscribe to a SQS/RabbitMQ somewhere, but in the meantime, to kickstart the service, I need to have a bunch of batch and dumps, and you can do all of that via events. It is a very interesting property. Now, the major two drawbacks of that is that actually writing code that works well in this kind of architecture is super hard. Just actually distributed systems in general are super hard. This is why there are like stuff like Symfony Messenger that try to help you. There are like stuff that we will cover that help you. But in general, it's hard, and it's probably harder to reason about for some teams. And actually, as well, the second complexity is that we sort of like go away from the normal things that we've been used to, being what is your API endpoint? Give me the request, give me the Swagger file, basically. If you give me the definition of the interface between services, and that's how we do the governance between services and between systems. That one with events is actually slightly trickier, because you still need to manage that, but you need to manage that in a way so that not everybody is allowed to publish anything and listen to anything either, because it can really, really be a mess. And without having a clear idea of like who consumes and who produces what, you might end up with that big bowl of mud of like plenty of services talking to each other, but having logic being completely spread across services. There's plenty of talk around that concept in distributed system, really, really about like, how do you basically apply DDD at the system level? That's not the point of this talk, but that's really something to look after if you go this path. And the last one is obviously, well, because, and especially if you use the property that I've mentioned of like having the message being stored by the bus, you need to have every single event being backward compatible. That's the short version. And that is also a faff. So you need to think about a bit. You need to anticipate these problems. So these are the main two drawbacks. There are plenty of situations where event streaming is not the right choice, especially when you don't have such as multi-services things, and when you don't need real time. But when you do, that is really fantastic. After you've started to set it up, it's really worth it. What I've mentioned is really that's the graphical version of what I mentioned. We have the various services sending their events to a bus, and then discount says, yes, I want to actually consume this message into something. But the idea is when we do the persistence, this is a graph, a drawing from a book called Data Intensive Applications, really recommended. The concept is that if you put all of these events or all these data point into these buses, well, then you actually are able to spread the load on like all the things that you want to do across many different workers. So typically you might have one worker that consumes all these events and push all of that into an Elasticsearch so you can search for your orders. You might have another one which actually push it to a specific time series because you want to do something, whatever. But you can really decouple and plug and play behaviors on top of what happens in your system without having to change the original producer of the event. Now that's about the theory. That's why even streaming is really valuable, and why at least you need to be aware of it. Now all the things we're going to talk, all the challenge that we're going to talk about are in the context of these architectures, but they are also completely true and already there if you just have one application which talks to one database, sends a bunch of stuff to RabbitMQ to a queue, and then have some workers. You already have all the problems we're going to talk about. So you might already be doing like event streaming without knowing it, or at least you already have these issues. So that's the fun part. What will go wrong? So we are going to use this very simple use case again of e-commerce. You have a Symfony controller that has an action which is called add product. What it does is that it will add the product to a basket. It will, where there is the kind of like commentary line, what it will do is just probably take a basket entity, add the product, save it to the local database. This is my new basket. And on top of that, it will use Symfony Messenger to dispatch a message. Let's say here, your own message, product added to basket. So it will do message bus, dispatch new product added to basket. And what you've configured within your Symfony application is that you've configured that this message, product added to basket, is going to go to this asynchronous transport. If you don't know Symfony Messenger, that is the way for Symfony to know that it needs to route this specific message, product added to basket, which is just one of your class, to route it to something. And the something is defined by this DSN, which can be RabbitMQ, Redis, Kafkas, and the likes. Now, that's the use case. Now, the problem A is, are you sure that the message was sent to the queue? What you're going to see as of now is all like drawings that I've made. Please tell me whether they are reasonable or not. I hope they are going to help you, but the end drawing is just mine, so it's not very straight, it's normal, and I'm sorry for that. So we have an example where we've got a bunch of users in the lab. They actually talk to our application that talks to our database, and then sometimes it sends a message to a queue. That's what we mentioned. Well, question to you, what happened when there is a fire at that moment? So the HTTP request, which is the user adding a product to a basket, arrived to our app. As I mentioned, it just updated the actual basket entity within the table to add this new product into the basket. And then it just crashed. For some reason, the machine burned or like something has happened or just a bug before it sends the message to the bus. What is the problem? Well, the problem is you might have an inconsistency here. You have something in your database, but you don't have it in the message, and all the underlying things that might happen later are not actually triggered. Well, what you should be able to tell me is that, hey, Sam, yes, obviously, if that happens, like everybody does, because we've wrapped everything into a database transaction, if there is an exception, we kind of roll back. So we are therefore able to roll back the right within the table. And I think that is the right answer, is to say, well, we need to care about that at the very least. That will fail sometimes. And I think that is really the main emphasis I want to say, is that it's not like, is it going to fail? It's really about when. So yeah, we can use a database transaction. That is great. So let's do that. What if actually it failed just when we were talking to the message bus? Well, at that moment, we already don't have a clue actually whether the message is in the bus or not. That's unlucky. What about it fails in here? What about it actually fails when I've wrote in the basket, I've actually sent it to the bus, and it fails now when I actually want to do something else in my database? Well, here I'm in a bad situation. Why? It's because actually I have this product. I will, if we use the transaction mechanism that we've discussed, I will actually have a message, product added to the basket in my queue, but then I will have rolled back database transaction and don't have anything in my basket table locally. That can be bad. That can be very bad. And obviously the same happens afterwards, right? If it's when you send back the request, the response to the client, you don't really know. So you have this problem that you cannot guarantee that you will have either everything has worked, everything is in the database and in the queue, or nothing has worked. So you will have inconsistencies. And the whole idea here is to say, well, actually, distributed transactions are not really a thing. This is a field that still has like really like fundamental research going on, but is such a mess. Having a transaction across multiple systems is really, really hard. So in the short version is that it's really not a thing. So what happens if you don't care? Well, I've mentioned to it, but like you have discrepancies between your local tables and your messages. And the most likely one is that you actually do not have something in your local basket table, but you have a message in the queue. Why is it a big deal? I think in our example, it doesn't matter too much. If we are talking about the fact that an event of the payment has been successful, or things like a fall has been detected in somebody's house or stuff like that, you do not have the luxury of saying, well, actually, it doesn't matter, because if we have 99.999 of the events, that's great, but the rest, or like the system is consistent for 99.9% of the time, that's great. There are examples of very business reasons where you just cannot. So what do we do? So how do you fix this problem? The solution to that one is called the outbox pattern. The concept is very simple. I mean, it really like blew my mind at the beginning because it's super simple, but it's a bit weird. So instead of actually doing this red arrow, which actually you took to the message queue, you actually don't do that. Rather, you are actually going to write into the same database that you have your basket table. You're going to write to what it's called an outbox table. This is a message I need to send to the queue. You write all your changes in your local tables and the message that you need to send, and you commit or roll back depending on the whatever issues or things that might happen in your service system. You commit and you roll back, or you roll back everything. Now that is great because once you've committed, you have now this other piece in the system, which is called an outboxer, or like something which is this little O square, which actually pulls the message from the outbox table. It can be every X milliseconds, or just if you use things like Postgres, you can have listens notify to notify directly the outboxer and so forth. And this outboxer's responsibility to send the message to the queue. Now, if something goes wrong between the outboxer and the queue, what happens? Well, the worst case is that we have multiple times the same message in the queue, because the outboxer sent the message to the queue, but actually something wrong happened in the network. It doesn't see it as sent, it sends it again. That's the worst case that can happen. So that's the first idea, that's the first concept and the first solution to the first problem. Now, talking about multiple messages at the same time. We have actually another alternative. We have an alternative, which is, well, maybe we can also not use such a queuing system. So maybe we actually don't talk to a RabbitMQ to actually send our messages, but actually we use the database for that. And I'm going to show you an example. So yeah, in a nutshell, you need to do every single stuff inside one single transaction, otherwise you have no control. With Symfony, you have another way, which is indeed to use the Doctrine transport for Symfony Messenger. What it does actually is that your images, you can do all the asynchronous stuff and have workers and things like that. But if you write everything, if you use the Doctrine transport, it means it will actually be written in the same Doctrine transaction, which means you don't have the consistency problem. So that's another example. That's another argument or like benefit of using the Doctrine transport within Symfony Messenger if you use it, rather than actually going to use a RabbitMQ or Kafka and all of that. If you don't need that, use the Symfony the Doctrine transport. You have less troubles. If you cannot do that, and if you really want to have a queuing system because you have various different services and so forth, then you have actually two main libraries or two main things that I've put links in the slides, which is a library from event source PHP, which is a kind of event sourcing library type of project for PHP, which has all the tools to do this outbox pattern. And you have one implementation of an outboxer, which is the second link, which is the thing that actually pulls messages from a table and sends it to whatever transport you might want. The Doctrine transport example in Symfony, it is basically the idea of saying, I want to configure my transport. Which type is it? This is the type Doctrine that uses the default entity manager. And we have a bus, which is our bus, to which we actually add explicitly, we need to add it explicitly, the middleware Doctrine transaction, which makes it so that you wrap everything, every process within the Doctrine transaction, every process of managing a message. Now, duplicate messages is the problem too, actually. So it turns out that when you consume stuff, you will receive multiple time duplicated messages. Not because the outboxer will can send it multiple times, but also because of another reason. And this other reason is called at least once delivery. This is the premise that we have with all of the queuing systems. Really, really, really all of them. The premise is you are going to receive every message that you publish to the queue is going to be received at least once by a worker. The translation of that is really that sometimes it will be received multiple times. An example is a worker here on your right, ask messages to the queue gives us message 1, worker process it, acknowledge it to the queue, gets message 2, process it, and then try to acknowledge it, and then something wrong happens in the system. There's a network failure or whatsoever. Well, the worker will start again probably, and then he will pull the message, and then it will get message 2. While it actually did process it, unfortunately. That is sad. That is sad, but that's exactly what will happen. In case of failure, whether on your side / the bus's side / inside in between, this will happen. So what can we do about it? Well, first of all, in our use case of the product added to basket, maybe we really, really don't need to do anything about it. So maybe it's completely fine. Maybe we will just compute that this product has been added to the basket only twice instead of just once, but it's not a big deal. But if it is a big deal, think around like, oh, there's this amount of money being added to your account, or oh, there's this medication that has been taken or whatsoever. If you do need to care about that, how do we deal with that? We need to apply this principle of idempotence. So the principle of idempotence is just to say, if I forgot the actual mathematical phrase. I had that at some point, but if you receive twice the same action or you do twice the same thing, it should result as the outcome or the output of the thing or the outcome of that is as if you've done it once. Basically, you know that you've handled it already, and then you ignore that second action if it worked well. So given you will receive the message multiple times, and it's just like a matter of like when will it happen, there is one key thing to note, which is that the actual framework, the symphonies of the world, there's really not that much that they can do about it. There is a little bit they can do when it's super high level frameworks, that data pipelines and stuff like that. Some of them can actually guarantee a really exactly once delivery, but for stuff in the PHP world and so on, we don't have such a thing. So you need to actually handle it in your application. That is sad. Now, how do you do that? You use an idempotency key. So the idea is that you have a key, you have an identifier that represents the fact that this is the message. This is not another one. So The concept being that, for example, when you have, I'll show you a bit of code later, but when you have the event that says product added to basket and that has a product ID and a basket ID, probably, you also want to have another property, which is probably the operation ID or the message ID that you can rely on the consumer side to not redo the same operation. A small parenthesis is that this principle of idempotence or idempotency is everywhere. Every single time you use an API, you will have the same problem actually. So Stripe Stripe's API is really a good example where when you ask, hey, charge £100 for this client, you can give them an idempotency key for the HTTP request, which might be something that you would pre-compute on your side usually. But then what it means is that if you actually do the same HTTP requests, charge £10 or 10 pounds or whatsoever 3 times with the same idempotency key, it doesn't matter. The client will not be charged 3 times. So yeah, it's a concept that actually is much broader than just workers and consumers. Now, so how it would look like, that's one option where you can actually just directly add the here I think is the operation ID within your actual message. That's one option. I think that's the best for me, just because it adds a little bit of sort of this bizarre ID within your message. It's not necessarily part too much of your domain. It's a bit of technical detail. I think it's good because it forces your team, everybody that sees this message, to understand why this thing is important and why we need to care about it. So how would you use it? Well, this is a extremely useful Symfony messenger handler that hypothetically will actually count the number of products of each type being added to a basket. So what we will do, we will actually register a message handler, which takes this event. You will actually get a basket. That's probably in another service or the same, it doesn't matter too much, but we'll get a basket entity from our database, for example, using Doctrine. We'll call this method product added and then save it to the basket repository. That's what our handler does. So all the logic or the thing related to idempotency will actually be within your domain model here. Now, how this thing would look like, this idempotent basket, well, it will look like so that this product added method, the first thing that it will do is that it would validate within the list of all the operation IDs that I have already registered, I have already handled for this basket. Is that new operation ID that you give me from the event, is it already in the list that is persisted in the database? If it is already in the list, I will just return and not do anything because I know that I've processed it. If it's not the case, I'm going to add it to the operation ID. That's what this function, I realized I actually probably need to explicit the code behind that add if not exists. It will just add the operation ID to the list if it doesn't exist, and it will return false so that it continues and does not return. It's a bit helper so you don't have too much faff in your code. But that's the simple idea. Is it already in the list? If it is, yes, I don't do anything. If it's not, I add it there. I know it will be persisted as soon as I've done something. That's the concept of idempotency. Again, you might not need to fix it. I will stop repeating that, but these are all the stuff that will happen on 0.01% or 0.0 something percent of your messages. It is down to you to understand whether you want to fix it or not. Now, that's great. We now have a system where events are sent consistently, and we managed to find that we have a accurate counter because we do have an idempotent process. Now, success is there. We scale. Hey, that's great. We're using workers. So the theory about using workers is that all you need to do is you put multiple of them, and then you scale. That is correct. But there is then new problems. Processing messages in parallel. So that is my most complicated diagram. I hope that you will like it very much. So from the queue, worker one gets a message. That's the blue thing. The blue gets the event. So the code that we saw, with the code that we saw, what will happen? Worker one gets the basket state from the database. That's the green square. Worker one, what does it do? Well, it will add, it create this kind of new basket by mutating it, by adding this new operation ID and counting and incrementing the number of products within this thing. That's great. Now, it turns out that because we are running in parallel, worker two also gets another message. It gets another event, another product added to basket. What does worker two does? Well, worker two asks the database, hey, give me the state of this thing. Give me the state of this basket. It gets the state back from the database. Now, what happens in time? Well, actually, what happens is that worker one now persists its state to the database. It's now its new counts of products and whatsoever. And you see where I'm going. Worker two, because it loaded the state before, what does it do? It adds its new events to the state, and then we have another list of operation IDs, and we have another counts, and then worker two saves the information to the database, and then you basically lost some data. And that data loss is probably even more big deal than what I've presented so far. So by that mechanism, with the code that we have right now, we are losing data, and that is potentially very bad. So what happens if you don't care about that? You lose some information. The easiest solution, again, do not process things concurrently if you don't need to. There's actually much more like literature recently about, well, actually, maybe just having an extremely simple flow of having really simple processes where we know that everything is done in this particular order is actually quite useful. So maybe you actually don't need to scale out to multiple workers. Especially workers, the interest is that if they fail, it's okay. They will just reboot and they will continue processing the messages. You don't necessarily need high availability in a way. Now, if you need to fix it, what happens? What do we need to do? Well, we need to do locking, and locking has two ways. The first one is the optimist. The optimist is to say, really, everything is going to be fine except a few use cases. And then the optimist, what it says is that, or what it does is that when it finishes process, it just validates. When it's stored information, it validates that nothing has changed in between the moment where it started to process the message and when at the end. So yeah. So basically here the optimist's trade-off is to say, I'm going to spend all the compute time because I really believe that it's super rare that there will be a conflict. So there is the equivalence, for example, HTTP's if match header. That's the kind of idea. Now the pessimist is the other way around. It knows that it's not gonna work. So before doing anything, you want to ensure that it's the only one doing anything for this basket, basically. So that, oh my God, and that is something you probably already know about, which is like the mutexes or Postgres's advisory logs and stuff like that. So before you do anything, you acquire some stuff, you hold to it, then the only one there, and then you do your process and you save, and then you release the lock. So the pessimist version with Symfony, there's a component for that actually called Symfony Lock. And what it would look like is in our handler, what we would do is we would have injected a lock factory service within this message handler in the constructor property of this class. And we will actually create a lock with a specific name at the beginning of when we start processing an event. The lock in this example is assuming that all the conflict that we have are associated to one particular instance of the basket. So actually the name of the lock is basket dash the basket ID, so that we know that there's plenty of basket being handled in parallel, but not two things in parallel for the same basket. What we do a lock acquire true. It means we actually start to acquire that's the blocking call, and it will wait until it's done is the only one there. And at the end, so that's the try finally, we release the lock so that other consumers can use this lock as well. That's the pessimistic version. Obviously, the trade-off is that I didn't mention in the previous slide, that this pessimistic approach makes it so that you need to have some IO, because you want this lock to be shared between all the workers. So you need to have something central, maybe a database, maybe a Redis, maybe a semaphore, something. you need to therefore do some IO network operations for every single of your events. And that is likely to slow down massively your requests, your throughput of workers. So then the second option is to say, hey, I want to be the optimistic. It's gonna work well. In our example, actually, all we need to do is to have a new field called version, or whatever you want to call it, a new field on our basket entity, and we are going to tag it with @ or m version. And that is the really super cool feature that's already shipped within Doctrine or M that you can use. How this thing works actually, and how you can implement it if you don't use Doctrine or M. Well, what it does is that when you do a save, it will not just do an update set values where ID equals. What it will do actually is that it will update your table, set the values for each field, set version equals version +1, where the ID equals the ID of your basket, and version equals a version number that we already have. And this version number is the version number that we add when we fetch the basket from the database. So what it means is that when we fetch the basket, we fetch the basket plus a pointer in time towards which the state that it is, i.e. the version number. When we save it in the database, we actually increase this pointer in time. And we save it only if the current pointer in time, which is the where version equals, if the current pointer in time in the database is the one that we've fetched before. If it's not the case, we throw an exception, and we have all the process that we've already discussed. Exceptions, we might roll back everything that we've done, and then we reprocess the message and we retry it. And that is optimistic locking. And with that, you're able to actually make sure that you will not have data being lost or corrupted by having multiple things writing to the same place. Now, the last piece is message ordering. That's my great latest picture here. You can see these fantastic dogs. My cat is nowhere near that. That's terrible. So you need to know that there is no ordering guarantee by default in most of the systems. So you will have a bus. I'm taking the example of RabbitMQ. You will have multiple producers, or even the same one. They put many different events to the bus, and you've got a worker, and the worker, even if it's just one worker, will just pick a message, get the green message, do it, get the actual blue message. Oh, it failed for some reason whatsoever. It might be that actually when it gets the next message, it gets the red one. It is completely possible. And then it will go back and actually get the blue one afterwards. So even in the way you actually receive within a single worker on the queue, there is most of the queuing systems that we have do not guarantee order. Now, obviously, when you scale, it's even like another faff that we're going to talk about, but you don't have an ordering guarantee. Now, when there is a failure, when everything goes well, it's usually it keeps the same order, but that's not the case when things burn. So hopefully your business logic just doesn't rely on the order of the events. I think the product added to Basket is a good example where we don't care. Just make sure it's true. We, for example, rely on stuff like events such as access granted and access revoked. And we actually say, well, yes, the access is being granted for this person to this other stuff. It turns out that if we have these two events, so somebody grants the access and just remove it straight away. If we have the order of these two events the wrong way, well, you can imagine what happens. You revoke an access that doesn't exist. Well, maybe you actually don't do anything for some reason. And then, bam, you actually grant the access after, which means that they have access to everything. That would be super bad. So there are examples where you actually need this notion of ordering. Now, there are buses that really infrastructure that guarantee order. SQS FIFO is a good example. Kafka is clearly one of them. We use Kafka and works quite well. The way it works is that within your what is called a topic, they have this idea of like commit offset. So actually, when you consume messages, what you do is that you don't get messages. You sort of just move a goalpost from all the messages that are in the topic, and Kafka knows that it needs to give to the consumer all the messages that are after this goalpost in that specific order. So that's how it works in partitions. The way it scales, in order, because you cannot guarantee order if you've got multiple workers on the same queue, because you have no clue of trying to understand which one will consume it first, right? Which one will do the data first. So you cannot scale ordering with multiple workers without splitting somehow your queues/topics. And the way the Kafka works and most of these systems work is that they split that in partitions. So for example, Kafka, when you create a topic, you actually need to tell it, this is the number of partitions that I want to have. Each partition will have an assigned consumer. You can have one consumer consuming from many partitions, but you can have at most one consumer per partition. And the guarantee of this system is that the order guarantee is only in this partition. What it basically means is that you need to have this notion of routing. You need to route all the messages that are relevant to each other in the same partition. Typically, in this access granted scenario, we want to have all the events associated to user A always in the partition 1, associated to user B always in partition B, for example. Yeah, we do that with partitioning keys. Traditional queues like RabbitMQ, queue, when we have like exchanges and queues, it's usually called the routing key. There's the same principle, same idea. Now, the problem with that is that it sounds great, but you will have massive troubles. And we had that, and it's not fun. And we didn't really design it really well up front, or we didn't thought that would happen. But basically, if you want to guarantee order, what happens is that you need to get to consume every single event in order. And what happens? Open question. What happens when you cannot process one message because the message is borked, because you've got a bug somewhere, because there is something, either on the producer or the consumer side? You are in a serious trouble. Why? It's because your consumer needs to do something about it. Does it discard the message? But if it does, well, you actually don't even guarantee order anymore. So in order to, so basically you need to deal with errors very well. So we've created an entire kind of framework on top of that, so that when there is an error, it will reroute all the messages belonging to the partitioning key that failed recently. I mean, it's really a faff. So that's something to take into account here if you really want to have ordering. Now, indeed, in order to have that infrastructure, so that's the summary, you need to actually have a queue, the queuing system that supports it. You really need to carefully design your partitions to know which partition, which message will belong to which partition, and you really need to be careful about managing all the errors. It will go wrong, and if you have like consumers being stopped for 3 hours because a bug in your code, that might not be the best. So to wrap up, hopefully a few learnings. If you want to publish a message service in a consistent manner, or like a strongly consistent manner, use the outbox pattern for the win. You will receive multiple times the same message, whether it's the outboxer's fault or whether that's the queue's fault. Idempotency is really important. When you consume multiple messages concurrently, do use optimistic or pessimistic locking. And then you can request, I really think this is the way of phrasing it. You can request ordering from your message infrastructure, but you really need to be then accountable to the fact that you need to design the partitions properly, and you need to have a way to manage errors. That's it. Thank you.